Hi there. This video is going to walk through an introduction to solving the Schrodinger equation for the hydrogen atom. Now, we've already looked at the hydrogen atom previously in the class. We've went through a whole discussion on the Bohr model and introducing the energy levels and had a pretty lengthy discussion about that already. So a lot of what we're going to end up with here should look familiar. But essentially what we're going to be doing is showing that we can arrive at all of those equations that we've worked with before and develop all of those quantum numbers and orbitals that you're familiar with simply by solving the Schrodinger equation for the hydrogen atom. So this is a really nice example to show kind of how powerful this whole quantum mechanics idea ended up being back when it was still in its infancy and people were still skeptical about it. So it's really kind of a nice cohesive example that shows that we do in fact end up with results that match our experimental results. Okay, so obviously one of the biggest triumphs of quantum mechanics was this solution to the Schrodinger equation for the hydrogen atom. Again, what's nice about it is that it's another problem that we can solve exactly. Okay, so you've noticed that we've been doing many examples that we know we can solve exactly. We'll quickly come to some examples where that's not the case. Okay, but we can solve the Schrodinger equation exactly for hydrogen and any other one electron system. Okay, so that's the key there. So those one electron systems are all going to have exact solutions with our Schrodinger equation. So your deuterium, helium plus, lithium 2 plus, and so on. Okay, and then for the physicists in the audience, the key here is that we are ignoring any relativistic effects. That adds another wrench into our problem. So we're going to leave that to the physicists, and we will stick with our non-relativistic hydrogen atom, which we will solve exactly. Okay, so another fun thing about being able to solve the hydrogen atom example is that all of our bonding theories that you're familiar with are based on solutions to this equation. So those valence bond theories, molecular orbital bonding theories, okay, all are based off of simple hydrogenic or hydrogen-like atomic orbitals. So we're going to see that down the road. And also the solution to the equation also gives rise to those quantum numbers, so N, L, and M sub L, and the orbitals, SPD and F orbitals that you know and love from Gen Chem and your other chemistry classes. So it's really just kind of going to bring everything that you took for granted for the last few years of your chemistry careers and kind of opening up where all of those concepts come from. And they come from solving the Schrodinger equation for the hydrogen atom. All right, so let's get started. So let's set up our problem just like we always do for a new system. So we need our quantum mechanical model for the hydrogen atom, and we model that as two particles. So we have our positively charged nucleus and a negatively charged electron that surrounds our nucleus. Okay, we're going to avoid the use of the word orbit, even though this, again, is kind of our best picture that we can draw right now. We know that that electron does not travel on that orbit due to our uncertainty principle, okay? But right now we're just modeling positive nucleus and negative electron orbiting some distance away. All right, so we have a classic two-body problem that we're working with, so that hopefully leads you to thinking about using a reduced mass. Okay, so we assume that we have a reduced mass moving about a central point at the center of mass between those two particles. And we are also going to factor in that attractive force that we have between our positive and negative charges here. So this is one of the biggest differences between our rigid rotor model, which was another two-body rotating kind of model that we just finished up with, where we assume there's no interaction between our particles. Okay, so here we know we do have that Coulombic electrostatic interaction between our nucleus, positively charged nucleus, and our negative electron. Okay, so we do have to factor that in to our model. So that gives us a potential energy that we did not have in our rigid rotor model. Okay, so that's a new addition here. Okay, so we have our electrostatic potential, or a Coulombic potential, that we're going to factor in here, which is given by this familiar expression from physics, where E is the charge on your electron or proton. Okay, they're very similar. R is going to be the distance between the proton and electron in your model, and E naught is our permittivity of free space. Okay, so one last thing that we can consider here is that because our potential has no theta and phi dependence, our potential is what we call spherically symmetric. All right, so that means that our potential just depends on the distance between our particles. Okay, so we have a spherically symmetric potential, which means we can be better off working in spherical coordinates rather than Cartesian coordinates. Okay, so we'll stick with our spherical polar coordinates for this problem as well, just like we used for our rigid rotor. Okay, so let's put together our Schrodinger equation for the hydrogen atom. Okay, so now that we've discussed our basic model, we can put together our Schrodinger equation. So we have our typical kinetic energy term. Remember, we have that del squared, that's our Laplacian operator that we saw before in the rigid rotor, same thing. Okay, we now have this additional potential energy term, okay, and then we have a wave function, okay, that is now modified slightly from our rigid rotor situation, where we have now a dependence on R as well as theta and phi. Okay, so hopefully you're starting to see the similarities between our hydrogen atom model and a rigid rotor that we've already completed. We're essentially just adding another layer onto the rigid rotor model, okay, in order to solve our hydrogen atom. So we still have this kind of rotating, spherically symmetric system. Okay, it's just that now we have a potential energy that we need to incorporate into our system, okay, and a dependence on the R, the distance between our particles, which we didn't have to do for the rigid rotor. Okay, so what we're going to end up doing, so we'll save the wave functions for another video, okay, but just kind of coming attraction, this form of our wave function, we're going to end up being able to split it up into a radial component and an angular component. So we're going to end up writing that as kind of a separable function where we have a factor that depends on R. We're going to call those our radial functions. And then we also have our angular part of the wave function, which we've already encountered. Okay, those are going to be our spherical harmonics that we've already worked with. Okay, so again, we'll save that, the details for the wave functions for another video, but just a coming attraction for you there. All right, so we can write this out fully with our del squared, our Laplacian operator, in spherical coordinates. So this should look familiar to you from back when we talked about, again, the rigid rotor and angular momentum topics previously. Okay, so we are essentially just not ignoring the parts that change with respect to R now. So before rigid rotor, we said that these terms, these DR terms, were 0, so we could ignore that. Can't do that anymore. Okay, so that's really the only difference in this system than what we've already looked at. All right, looks nasty still, hasn't gotten any better, but we can make it a little bit more manageable by doing a little bit of trickery. So if we multiply by 2 mu r squared, okay, so essentially getting this term out of that denominator, we end up with this expression, which might not immediately look any better to you, but it turns out that that middle term corresponds to L squared. Okay, so this whole chunk right here in the middle is actually our total angular momentum squared operator that we've already worked with. Okay, so we can simplify then our Schrodinger equation a little bit to this bottom equation here. Okay, and if you look closely, you'll see that we can separate our Hamiltonian essentially into one component that depends on R only and a component that depends on the angular parts, the theta and phi only. Okay, so this term is all R. This term is all R. Okay, and then this middle term here is where those angular components live, the theta and phi. Okay, so everything is separated. We don't have any interactions essentially between the R or the theta and phi parts. Okay, so what we essentially end up with here is what we call a separable Hamiltonian again. Okay, so it's just like what we saw when we looked at our other multidimensional systems where we could separate out the X component from the Y component from the Z component, okay, and kind of treat them all separately. Okay, it's the same idea here, except we've got a radial component, so depending on R, and our angular component, which depends on the theta and phi. Okay, so we've basically got one part that we've already figured out. Okay, so don't forget, we already did this part. Okay, we've already looked at our angular momentum and spherical harmonics. Okay, so half the work is done. So the only part that we need to work with now is to figure out that radial part to get those radial functions. Okay, and it's kind of a neat trick, a neat fact that in general the spherical harmonics turn out to be the angular factors of any wave function involving a spherically symmetric potential function. Okay, so you'll find that those spherical harmonics pop up a lot in other natural systems or other mathematical or physical systems whenever you have a spherically symmetric potential. Okay, so this last bit is just a summary of what we end up with when we solve that Schrodinger equation. So right now we've really only set it up. We'll take a closer look at the solutions in a separate video, but just to give you the good stuff right away that you can work with. The wave functions we've already mentioned can be written out as a product of 3 functions. Okay, so we have our radial component, we have our theta component, and our phi component. Okay, so remember these parts are just your spherical harmonics again. Okay, we see that we have dependence now on 3 quantum numbers. Those quantum numbers again arise naturally out of solving the Schrodinger equation for these different parts of our wave function. Okay, so we've already encountered the L and the M sub L, right, when we did our spherical harmonics. Okay, our new quantum number that arises naturally out of our solutions is our N. Okay, remember this is your total energy quantum number or your principal quantum number. Okay, we're going to see that that arises from solving those radial functions. Okay. All right, so those are the wave functions that we're going to be working with for the hydrogen atom. And then you'll also see in solving the Schrodinger equation that we end up with allowed energy states that, again, are dependent on n, so we get those quantized energy states. And if you go back and look at your notes from way back at the beginning of the semester, you should see that this equation looks familiar. Okay, so this is exactly the same equation that we were working with before, okay, where before it was kind of just an ad hoc sort of, hey, this happens to work out kind of equation, and now we end up with it arising naturally from solving our Schrodinger equation. Okay, so quantum mechanics really seems to be working for us, okay? And just one last side note before we finish up. When we talk about energies as quantum chemists, especially if you're a computational chemist, you tend to use some alternative units. So normally chemists, we like to use units of joules or SI unit for energy. Okay, quantum or computational chemists will often use energy units of Hartrees, which have that symbol E sub H. Okay, and so this is just our definition of a Hartree. So it has a symbolic definition here with all of our constants. Okay. You can have it also in units of electron volts. That's another popular energy that you'll see floating around with a lot of these calculations on for atomic and molecular energies. And then you can also see how it relates to our SI unit of the joule. Okay, so that might come in handy for you depending on the situation that you're in. All right, so that was a quick summary of how to set up the Schrodinger equation for a hydrogen atom and a preview of the solutions that you end up with when you solve that Schrodinger equation. And stay tuned for another video where we talk about those wave functions in a little bit more detail. All right, thanks.